external to the compiler, but which I think have a very high motivational value for using some concepts in a language. So let's take a step back into something called software product lines. And in a study by the Software Engineering Institute at CMU, there's some remarkable figures about the benefits you can achieve with software product line development. So you get 10 times speed up in the development process, you get a factor of 10 in productivity, quality, and you cut down development times quite a lot. So these numbers seem quite impressive and may sort of seem unrealistic in some sense. Our experience with domain-based developments show that these aren't unrealistic. They may not sort of fit every project, but we're seeing numbers which sort of makes us believe that this can be true. So what is the software product line? It's a family of software entities which are developed together, which sort of relate to a specific market domain. They're created from a common set of assets, core assets, which mostly is architecture, it's libraries, it's test tools, and project planning, sort of lots of things which work together and creates a high reuse, and therefore it is beneficial. Core asset development is often called domain engineering. We try to sort of look at all problems in the domain and not just one specific application. And application development is application engineering, which is targeted to a specific application and its requirements. So to get the benefits of this, you need to do domain engineering before you start the individual application engineering. And there's sort of a high initial cost, but then the benefits you get afterwards means that the cost per application is much lower. These studies sort of say that if you develop more than 3 applications in a domain, it's worthwhile doing it. And the more aggressive you do your domain engineering before you start your applications, the higher the turnoff as you move into application number 4, 5, 6, and onwards. If you try to sort of hack it from an application and then sort of slowly move into domain engineering, your payback is going to be less, even though your economies or sort of having some income all the time may be better. So what is domain engineering? Defining your core assets. Well, for me it's sort of finding something in the language of software. And there's this old book titled Magne, Algorithms plus Data Structures equals Programs, which for me then says that, well, we need to understand the types, we need to understand the functions, and we need to understand the properties we are looking for. So type has, in this sense, an abstract equality function, which may or may not correspond to a concrete algorithm in C++, for instance, with the equal. So there's many things, sort of technical issues we can discuss. For defining the properties, I'm going to use kind of predicate notation, very simple assertions. In these examples, I'm using basically equality to sort of state the properties. So the questions we need to ask on the domain then is, what are the types? What are the functions we want to have? What are the axioms that belong to those functions? Basically, we need to define what is known as C++ concepts, where we declare these things and we are able to write down the properties. So here's a small example where we define a monoid, and the notation I'm using is not compatible with any proposed concept notation, so don't take that too seriously. So there's this axiom which defines associativity, and then there's a couple of axioms which define what neutral means. Now I can, for instance, use the axiom of associativity to test that if I have some binary operation, and it should be monoid, that actually the assertion holds for collection of input data applied to that function. Likewise, I can check the neutral axiom and see if the selection of input values correspond to the correctness of these axioms, and therefore test that my functions actually behave as you expect them to behave. The other thing I can do is sort of think about this as a rewrite rule. So if I have an expression of this form, replaced by the simpler expression corresponding to the variable data set. So I can use the information in an axiom for many different purposes. I can use it for understanding what I'm looking at. I can use it to test what I'm implementing. I can use it to optimize, transform the code I'm working with. I'm also going to talk a little bit about data structure algebra. So if we have different ways we can lay out a data structure, we can sort of have correspondences between them. And one of the simplest thing to think about is isomorphism, which intuitively says that two different data declarations have the same information content. So you can basically translate all the information from one to the other and back again and get everything. So here's on the left classical, what I did in my Fortune days, 1477, where you had sort of two arrays containing information, A of 100 and B of 100 elements. And that was my data, and I had to index into that. Implicitly, I was thinking that element AI and element EI corresponded to the same abstraction, but wasn't visible in the code. On the right, I have a more modern form, where I can say I have a structure which connects A and B as a unit, and I can reason about A and B together as some abstract entity, and then I have a collection of 100 of these. So I can dot and index into this data, get the same information, and back and forth. So they have the same content, but have different access patterns. More importantly, they represent different abstractions. We can use them for different purposes, and they have different properties when it comes to my reasoning about software, the development of software, and how I will use the components in my software. So thinking about this is quite important. So I thought I would move on to a practical example. The heat problem. So in Norway, wind takes cold outside. We come home after work, we switch on the heat pump, and when it sort of heats up inside, we get happy because we can take off the sweater and sort of relax and feel at home. In Texas, there's another heat problem. It's hot outside, the sun is shining, the air conditioner is running at full, and we're happy when we have the sweater on. And during the day, it becomes hotter and hotter, and it heats up inside as well, and we get unhappy because everything is sort of. So it's sort of two variations of heat problem, but they're sort of described with the same mathematical entities. So at the lower left, there's a cross-section of the wall, sort of separates the warm part from the cold part. And if we're trying to understand what's going on in this world, I need to sort of understand how the temperature is distributed across the wall. So we have lots of grid points where we're trying to sort of measure the temperature, sort of simulate the knowledge of what the temperature is supposed to be. And for instance, if I take a cross-section like this, we'll have temperature curve on the left side, it's cold on the right side, and there's a gradient between, sort of dropping from hot to cold. Now, on the top right, you see an equation which sort of describes how heat distributed in space relates to changes in heat distribution in time. And this is another physical equation describing the physics of heat transfer inside the wall. Now, trying to analyze this problem from a software point, I'd sort of start asking questions: what are the types, what are the functions, and what are the behaviors we're looking at? And in the variables I have is the variable u, which describes the temperature at every point in the wall throughout time. And then there's this derivative, after the derivative of time, so it says what's the rate of change in temperature at a specific point in time. I have alpha, which describes how heat moves through the various positions of the wall, because the wall is made of different material, and therefore heat diffuses more rapidly or slowly through the different parts. So you have good insulation, which will keep a steeper gradient than if it's sort of just plain metal. So looking at this, I have something which is called scale fields, which are these values at every point in space. I have these derivation operations, which will look at a point and its neighbors and trying to see how the gradients are, how changes in the temperature and heat flow are working. And I have simple scale operations, which do multiplication of every point in space, the value of every point in space, or addition of every point in space. And also I have scalar valued, what's the scalar field? Scalar valued point, but I also have points which have vector values and matrix values, which sort of describe what's going on at that point. So that sort of gives me the basis for some declarations of abstractions. So there's a simple concept for the arithmetic operations, addition, multiplication, constants like 0, minus, and I sort of put out the basic axioms for the ring. Now we know that real and complex numbers are rings with units in the mathematical sense, not on the computer. Let's just stick with idealized mathematics here. But also the scalar field is a ring because it behaves like a ring if you do the pointwise operations, adding together the value at the same point in two different scalar fields behaves as addition in the ring. So I can sort of create the ring out of my scalar operations. I can take a look at the matrix, and the matrix also behaves as a ring. So I sort of get lots of things that are ring-like structures. And if I look at how I can build things, I can see that I can build scalar field. If I have a ring element type, I can build a scalar field which at every point has a ring value, and that will behave as a ring. So the simplest thing I have is a data field which has basic type R, and at every point in the data field I can ask what is the value at that point, and that's a value type R. The scalar field says that the value R of type R is a real number, so we get a real number at every point. And I can do addition, subtraction, multiplication, since the real number has ring properties, and therefore I propagate the ring properties to the scalar field. But also have partial derivatives. So I can look at the change of time, the change of the x-axis, the y-axis, the z-axis, or the other directions I'm interested in. I said that I could have a matrix data type, and I can create a matrix out of any ring type R, and then I get a matrix data type which behaves as a matrix with addition, subtraction, matrix multiplication, and other operations that related to that. So I said that I may need a matrix field, that is a field in space which has a matrix at every point. I'm thinking about how to declare this data structure. I have two alternatives. I can take a matrix with the real values at the point, and then I can replicate this for every point in space. That is the top line, the data field with matrices at every point. Alternatively, I can say, well, let's take a matrix structure and put the ring, which is the scalar field, with a real value at every point. And these have the same information content, because if I have an index into an element of a matrix, and I have a point, first I look at a point, I get a matrix, and use the matrix index, I get the real value corresponding to that component of the matrix at that point in space. The second declaration says that, okay, I have a matrix, I use the matrix index, I get an element. The element is a scalar field, the index is a scalar field with the point I'm looking at, and I get the component of the real value corresponding to the component of the matrix at that point. So from this information viewpoint, these two data structures are isomorphic. I can use them interchangeably if I just want to keep the information that's there. But if I want to look at the algorithmic things I'm put on top of this, I need to put the addition, multiplication, matrix multiplication operations. Those go fine because those are lifted from points and both data structures behave the same. If I look at the partial derivatives need to look at the neighbors. Looking at the neighbors means that I need to sort of understand what's going on in the data field, and I need to know about the matrix operations if I use the top version. If I use the bottom version, I can use the construction of the derivatives, like the gradient and the divergence, from the partial derivatives directly on the scalar field. So that means that the scalar field representation, the lower one, I can choose the representation of the scalar field provided partial derivatives, and the matrix field doesn't need to know about the representation of the scalar field. In the top version, the data field of matrices, the data field needs to know about the representation so that I can create derivative operations on top of the field. So it sort of gets complicated. I cannot abstract away how it represented point values and the connection. So from this viewpoint, the scalar field of Gaussian derivatives is better when I want to construct my code, because I can reuse components rather than having to duplicate the derivative operations as I move outwards in my abstraction memories. If you look at conventional numerical code, they typically use the data field and matrix representation. Well, in this analysis, you see that the matrix of scalar field has much better properties as a software entity. And this is the kind of analysis we're able to do and looking at things from the viewpoint of domain engineering and not just diving into it, building specific applications. Now there's another problem which appears in this kind of mathematics, and this is ousted when I try to use axioms to understand what's going on. So if you ask a typical applied mathematician what the dot product is, physicist, they will just say, well, take two vectors, you add, multiply together the corresponding components of the two vectors, and then you add everything. Which is sort of a simple loop like the summation sign. Then they talk about change of basis in vector space. We can encode that as a matrix which represents the coordinate system, and you multiply that with a vector and create a new vector which represents the same vector in the new coordinate system. So the vector as a physical entity is here, but we sort of can decide that changing the coordinate system, so the values representing the vector changes, but it's the same vector. Now, from a physical viewpoint, the dot product represents property of the vector, or property of the relationship between two vectors, which do not change. The two vectors are given space, and if I change the representation of the two vectors, it doesn't change the two vectors. So when we're looking at the property which is defined by the dot product, that should not change if I change the coordinate basis. So then I can write this axiom here, saying that for dot of uv, or dot of u and v after coordinate change should be the same abstract value, because that's a measurement of the relationship between these two vectors. Now, this breaks down, because when I change the coordinate system, I change the values of the vectors, and the dot product gives me a different value. So, I may ask the question, what's wrong here? Is the dot algorithm wrong? Is the typing wrong? Or is the change of the coordinate system wrong? Or is there some interaction between these things? So, talking to people in more sort of pure mathematics, they would say that, well, the dot algorithm is wrong because you need to take the coordinate system into account, and therefore you should have put the matrix representing the coordinate system inside the dot product and use that to correct for the algorithm. And other people will say, well, it's the typing. The dot product isn't really between vector and covectors. Vector and vector is between vector and covector. The covector changes differently when you change your basis. So therefore the top algorithm is okay if one is a vector, the other is a covector. You need to add another function for changing the covector component, and then therefore the equation will hold. Now if you look at these two people, one is saying, well, the algorithm is wrong, the other is saying the typing of the algorithm is wrong. And basically that, for me, that means that we're actually talking about two different functions. We're talking about one function which is between two vectors, which has a different algorithm. And in some coordinate systems, they will coincide with this algorithm. The other is a retyped version of the dot product with the same algorithm, but with different typing of the variables so that we can use the algorithm whatever the coordinate system is. So what appeared to be one function now becomes two distinct functions with distinct algorithms which coincide in many cases. And this is something I've seen in many other domains when we try to do this kind of analysis, is that somehow the notion of function isn't just one function, it's actually a collection of different functions which are closely related at the conceptual level, but which have distinct different properties and try to write down the properties. If you try to just write down one case or the other case, it actually coincide, because it's a common case where they coincide, but the axioms you write down for them actually turn out to be different. Therefore you need to sort of look at the typing, you need to change things which commonly are confused. And vectors and covectors are commonly confused in math because they both have the same representation, and in many coordinate systems they behave exactly the same, but they can behave differently if you start looking at it. This is the kind of analysis I seem to be able to do and try to write down the concepts, make them precise, and then get them back to what I'm doing. I'm getting conscious about what's going on and getting more information on the domain. Here's another example of seismic waves. These are very important when you're looking for oil, which I guess is something people do around Texas and in Norway. Again, the equations are different. If you look at the variables, I'm dealing with vector fields, scalar fields, matrix fields. The operations, some are the same, some are different, but the structure of the problem is the same. So just don't really need to add anything to the architecture we're looking at, just need to expand the library with some more functions. And this sort of thing will work on more and more problems. You can see that it's the same structure going again. You're not discovering new types, you're just discovering new operations which are quite easy to put into a library. So in some sense, by looking carefully at a few examples, asking people who know what's going on, we're able to oust this information and using the concept as a tool in trying to make things precise. So the initial conclusion, domain engineering defines core assets of the software domain. It's essential in order to develop software pipelines which are useful for high reuse and low costs for developing new applications. And domain engineering precedes application engineering in this style of thinking. C++ style concepts are very useful as a tool for asset development. So the libraries, we identify the functions, the types, the axioms, and the axioms help you drive towards more comprehensive API, which turns out to be more usable. Add extra functions to it because it's easier to specify with some extra functions. And with more functions in the API, it can be used in more contexts. So that's one of the experiences we've had. We're trying to do concept-based analysis, we get more functions in APIs. We can do these architectural considerations that I was talking about, using isomorphism, the same information content, but different abstracting properties, and use that to get better organized software domain. It is very important to get the high benefits in improved productivity when it comes to software development. And then we have the tool side of this. Axioms can be used as test oracles. We've written some papers on that where we aggressively feed axioms with random data to see how the implementations behave as expected. And also, as Bjarne mentioned initially, we can use equational axioms as refactoring tools for organization purposes, program organization purposes as well. So I think I'll conclude there.
It has a significantly different form for vector operator in a linear domain. And it also involved in the health transformation of word transformation. It has different form. And it also maybe involved in simple grid or staggered grid if you are talking about the prime difference method. So my question is, did you use C++ concept to generalize these ideas for vector field and its vector operator? And the second question is, do you use C++ concept for numerical scheme? I mean, or you just find everything, type everything finite difference, or yeah, I have two questions.
What we did was actually about 20 years ago. 20 years ago? Yeah, close to 20 years ago. So we didn't have C++ fields have scalar fields as components. Matrix fields have scalar fields as components. Arbitrary tensors have matrix fields as components. This seems to have been very stable. We've been looking at very many problems after that, and the architecture we came up with has been very stable across these. I used sort of the notion of the finite difference method as a simple way of understanding you're looking at gradients and other things which cross over from one point to larger parts of the domain. We've used this initiation principle also for finite volumes and finite elements, and it seems to work. We don't need to change the basic architecture, even though the implementation of the scalar field changes. We need to do more complicated time integration methods, but it doesn't tend to change the architecture. Things fit together. Yes?
The example you gave were pretty nice because it covers all of these mathematical ideas that have been very well studied for centuries. And have you looked at any domains that, like reprogramming, or have you tried to apply these to anything beyond something that's so heavily mathematical? I mean, it's all naturally mathematical.
Yes, I'm using axiom-based programming for most of my work now because it really helps me to clarify the APIs developing software. So I've been using this for an exhibit we're putting up for Science Center, which is multi-threaded and deals with communication, so intestinal communication protocols that actually move data in the way you expect. We tested that on all the SMILey units we're having, working the right way, and in a couple of occasions we've seen that what we thought was one function actually has to be several different functions. So that's sort of a non-mathematical domain in that sense. Yes, it seems to give a benefit in all kinds of areas. And even though mathematics has been for centuries, what we found out was that the conventional way of writing software wasn't ideal for that architecture because you had to replicate lots of internal information across the whole software system. So we can say, well, the basic knowledge of what's going on has been there for quite some time, but the organization of software in that domain hasn't really matured that much. Reasons up to the century, reasoning, but that can also be historically people weren't solving problems with computers. So in the first few centuries of this, they were doing things by hand, which means that we're looking at things from a different perspective. When you sort of put things into 100,000 lines of code, the text itself becomes important, and doing things in different pages of math because it will internally rearrange and try a way to access data without changing anything because it's all inside your head and doing the calculations.
I guess what I was getting, like, so the siloed reasoning is the same, right? That we found across like applied mathematics and
these are the things, yeah. So asking these questions, what are the types, what are the functions, what are the axioms, really seems to clarify things and how to sort of have a confused two ideas, can make things simpler. And in many cases we have sort of large run methods in Java, we split them up into several classes and a much simpler run method. To test the classes, and the run method was sort of something we could reason about. The original run method we couldn't reason about it, we just hope. And testing it was basically possible because we needed a full framework around it to do the test. Separate